Solar energy is radiant light and heat from the sun harnessed using a range of ever-evolving technologies such as solar heating, photovoltaics, solar thermal energy, solar architecture and artificial photosynthesis. It is an important source of renewable energy and its technologies are broadly characterized as either passive solar or active solar depending on the way they capture and distribute solar energy or convert it into solar power. Active solar techniques include the use of photovoltaic systems, concentrated solar power and solar water heating to harness the energy. Passive solar techniques include orienting a building to the sun, selecting materials with favorable thermal mass or light-dispersing properties, and designing spaces that naturally circulate air. The large magnitude of solar energy available makes it a highly appealing source of electricity. The United Nations Development Programme in its 2000 World Energy Assessment found that the annual potential of solar energy was 1,575–49,387 exajoules. This is several times larger than the total world energy consumption, which was 559.8 EJ in 2012. In 2011, the International Energy Agency said that the development of affordable, inexhaustible and clean solar energy technologies will have huge longer-term benefits. It will increase countries' energy security through reliance on an indigenous, inexhaustible and mostly import-independent resource, enhance sustainability, reduce pollution, lower the cost of mitigating global warming, and keep fossil fuel prices lower than otherwise. These advantages are global. Hence the additional costs of the incentives for early deployment should be considered learning investments. They must be wisely spent and need to be widely shared. Potential. The Earth receives 174,000 terawatts of incoming solar radiation at the upper atmosphere. Approximately 30% is reflected back to space while the rest is absorbed by clouds, oceans and land masses. The spectrum of solar light at the Earth's surface is mostly spread across the visible and near-infrared ranges with a small part in the near-ultraviolet. Most people around the world live in areas with insolation levels of 150 to 300 watt per square meter or 3.5 to 7.0 kilowatt-hours per square meter per day. Solar radiation is absorbed by the Earth's land surface, oceans, which cover about 71% of the globe, and atmosphere. Warm air containing evaporated water from the oceans rises, causing atmospheric circulation or convection. When the air reaches a high altitude, where the temperature is low, water vapor condenses into clouds, which rain onto the Earth's surface, completing the water cycle. The latent heat of water condensation amplifies convection, producing atmospheric phenomena such as wind, cyclones and anticyclones. Sunlight absorbed by the oceans and land masses keeps the surface at an average temperature of 14 degrees Celsius. By photosynthesis, green plants convert solar energy into chemically stored energy, which produces food, wood and the biomass from which fossil fuels are derived. The total solar energy absorbed by Earth's atmosphere, oceans and land masses is approximately 3,850,000 exajoules per year. In 2002, this was more energy in 1 hour than the world used in 1 year. Photosynthesis captures approximately 3,000 EJ per year in biomass. The amount of solar energy reaching the surface of the planet is so vast that in 1 year it is about twice as much as will ever be obtained from all of the Earth's non-renewable resources of coal, oil, natural gas, and mined uranium combined. The potential solar energy that could be used by humans differs from the amount of solar energy present near the surface of the planet because factors such as geography, time variation, cloud cover, and the land available to humans limits the amount of solar energy that we can acquire. Geography affects solar energy potential because areas that are closer to the equator have a greater amount of solar radiation. However, the use of photovoltaics that can follow the position of the sun can significantly increase the solar energy potential in areas that are farther from the equator. Time variation affects the potential of solar energy because during the nighttime there is little solar radiation on the surface of the Earth for solar panels to absorb. This limits the amount of energy that solar panels can absorb in one day. In addition, land availability has a large effect on the available solar energy because solar panels can only be set up on land that is unowned and suitable for solar panels. Roofs have been found to be a suitable place for solar cells, as many people have discovered that they can collect energy directly from their homes this way. Other areas that are suitable for solar cells are lands that are unowned by businesses where solar plants can be established. Solar technologies are broadly characterized as either passive or active depending on the way they capture, convert and distribute sunlight and enable solar energy to be harnessed at different levels around the world, mostly depending on distance from the equator. Although solar energy refers primarily to the use of solar radiation for practical ends, all renewable energies, other than geothermal and tidal, derive their energy from the sun in a direct or indirect way. Active solar techniques use photovoltaics, concentrated solar power, solar thermal collectors, pumps, and fans to convert sunlight into useful outputs. Passive solar techniques include selecting materials with favorable thermal properties, designing spaces that naturally circulate air, and referencing the position of a building to the sun. Active solar technologies increase the supply of energy and are considered supply-side technologies, while passive solar technologies reduce the need for alternate resources and are generally considered demand-side technologies. In 2000, the United Nations Development Programme, UN Department of Economic and Social Affairs, and World Energy Council published an estimate of the potential solar energy that could be used by humans each year that took into account factors such as insolation, cloud cover, and the land that is usable by humans. The estimate found that solar energy has a global potential of 1,575–49,837 EJ per year. Thermal energy. Solar thermal technologies can be used for water heating, space cooling and process heat generation. Early commercial adoption in 1897, Frank Schumann, a U.S. inventor, engineer and solar energy pioneer, built his small demonstration solar engine that worked by reflecting solar energy onto square boxes filled with ether, which has a lower boiling point than water, and were fitted internally with black pipes which in turn powered a steam engine. In 1908, Schumann formed the Sun Power Company with the intent of building larger solar power plants. He, along with his technical advisor A.S.E. Ackerman and British physicist Sir Charles Vernon Boys, developed an improved system using mirrors to reflect solar energy upon collected boxes, increasing heating capacity to the extent that water could now be used instead of ether. Schumann then constructed a full-scale steam engine powered by low-pressure water, enabling him to patent the entire solar engine system by 1912. Schumann built the world's first solar thermal power station in Mahdi, Egypt, between 1912 and 1913. Schumann's plant used parabolic troughs to power a 45 to 52 kilowatts engine that pumped more than 22,000 liters of water per minute from the Nile River to adjacent cotton fields. Although the outbreak of World War I and the discovery of cheap oil in the 1930s discouraged the advancement of solar energy, Schumann's vision and basic design were resurrected in the 1970s with a new wave of interest in solar thermal energy. In 1916, Schumann was quoted in the media advocating solar energy's utilization, saying, We have proved the commercial profit of sun power in the tropics and have more particularly proved that after our stores of oil and coal are exhausted, the human race can receive unlimited power from the rays of the sun. Frank Schumann, New York Times, July 2, 1916. Water heating. Solar hot water systems use sunlight to heat water. In low geographical latitudes, from 60 to 70% of the domestic hot water use with temperatures up to 60 degrees Celsius can be provided by solar heating systems. The most common types of solar water heaters are evacuated tube collectors and glazed flat plate collectors, generally used for domestic hot water, and unglazed plastic collectors used mainly to heat swimming pools. As of 2007, the total installed capacity of solar hot water systems is approximately 154 thermal gigawatt. China is the world leader in the deployment with 70 GWth installed as of 2006 and a long-term goal of 210 GWth by 2020. Israel and Cyprus are the per capita leaders in the use of solar hot water systems, with over 90% of homes using them. In the United States, Canada and Australia, heating swimming pools is the dominant application of solar hot water, with an installed capacity of 18 GWth as of 2005. Heating, cooling and ventilation. In the United States, heating, ventilation and air conditioning systems account for 30% of the energy used in commercial buildings and nearly 50% of the energy used in residential buildings. Solar heating, cooling and ventilation technologies can be used to offset a portion of this energy. Thermal mass is any material that can be used to store heat from the sun in the case of solar energy. Common thermal mass materials include stone, cement and water. Historically, they have been used in arid climates or warm temperate regions to keep buildings cool by absorbing solar energy during the day and radiating stored heat to the cooler atmosphere at night. However, they can be used in cold, temperate areas to maintain warmth as well. The size and placement of thermal mass depend on several factors such as climate, daylighting and shading conditions. When properly incorporated, thermal mass maintains space temperatures in a comfortable range and reduces the need for auxiliary heating and cooling equipment. A solar chimney is a passive solar ventilation system composed of a vertical shaft connecting the interior and exterior of a building. As the chimney warms, the air inside is heated, causing an updraft that pulls air through the building. Performance can be improved by using glazing and thermal mass materials in a way that mimics greenhouses. Deciduous trees and plants have been promoted as a means of controlling solar heating and cooling. When planted on the southern side of a building in the northern hemisphere or the northern side in the southern hemisphere, their leaves provide shade during the summer, while the bare limbs allow light to pass during the winter. Since bare, leafless trees shade 1/3 to 1/2 of incident solar radiation, there is a balance between the benefits of summer shading and the corresponding loss of winter heating. In climates with significant heating loads, deciduous trees should not be planted on the equator-facing side of a building because they will interfere with winter solar availability. They can, however, be used on the east and west sides to provide a degree of summer shading without appreciably affecting winter solar gain. Cooking. Solar cookers use sunlight for cooking, drying and pasteurization. They can be grouped into three broad categories: box cookers, panel cookers and reflector cookers. The simplest solar cooker is the box cooker, first built by Horace de Saussure in 1767. A basic box cooker consists of an insulated container with a transparent lid. It can be used effectively with partially overcast skies and will typically reach temperatures of 90 to 150 degrees Celsius. Panel cookers use a reflective panel to direct sunlight onto an insulated container and reach temperatures comparable to box cookers. Reflector cookers use various concentrating geometries to focus light on a cooking container. These cookers reach temperatures of 315 degrees Celsius and above but require direct light to function properly and must be repositioned to track the sun. Process heat. Solar concentrating technologies such as parabolic dish, trough and Scheffler reflectors can provide process heat for commercial and industrial applications. The first commercial system was the Solar Total Energy project in Shenandoah, Georgia, USA, where a field of 114 parabolic dishes provided 50% of the process heating, air conditioning and electrical requirements for a clothing factory. This grid-connected cogeneration system provided 400 kilowatts of electricity plus thermal energy in the form of 401 kilowatts steam and 468 kilowatts chilled water, and had a 1-hour peak load. Thermal storage. Evaporation ponds are shallow pools that concentrate dissolved solids through evaporation. The use of evaporation ponds to obtain salt from seawater is one of the oldest applications of solar energy. Modern uses include concentrating brine solutions used in leach mining and removing dissolved solids from waste streams. Clothes lines, clothes horses, and clothes racks dry clothes through evaporation by wind and sunlight without consuming electricity or gas. In some states of the United States, legislation protects the right to dry clothes. Unglazed transpired collectors are perforated sun-facing walls used for preheating ventilation air. UTCs can raise the incoming air temperature up to 22 degrees Celsius and deliver outlet temperatures of 45 to 60 degrees Celsius. The short payback period of transpired collectors makes them a more cost-effective alternative than glazed collection systems. As of 2003, over 80 systems with a combined collector area of 35,000 square meters had been installed worldwide, including an 860 square meters collector in Costa Rica used for drying coffee beans and a 1,300 square meters collector in Coimbatore, India, used for drying marigolds. Water treatment. Solar distillation can be used to make saline or brackish water potable. The first recorded instance of this was by 16th-century Arab alchemists. A large-scale solar distillation project was first constructed in 1872 in the Chilean mining town of Las Salinas. The plant, which had solar collection area of 4,700 square meters, could produce up to 22,700 L per day and operate for 40 years. Individual still designs include single slope, double slope, vertical, conical, inverted absorber, multi-wick, and multiple effect. These stills can operate in passive, active, or hybrid modes. Double slope stills are the most economical for decentralized domestic purposes, while active multiple effect units are more suitable for large-scale applications. Solar water disinfection involves exposing water-filled plastic polyethylene terephthalate bottles to sunlight for several hours. Exposure times vary depending on weather and climate, from a minimum of 6 hours to 2 days during fully overcast conditions. It is recommended by the World Health Organization as a viable method for household water treatment and safe storage. Over 2 million people in developing countries use this method for their daily drinking water. Solar energy may be used in a water stabilization pond to treat wastewater without chemicals or electricity. A further environmental advantage is that algae grow in such ponds and consume carbon dioxide in photosynthesis. Although algae may produce toxic chemicals that make the water unusable. Electricity production. Solar power is the conversion of sunlight into electricity, either directly using photovoltaics, or indirectly using concentrated solar power. CSP systems use lenses or mirrors and tracking systems to focus a large area of sunlight into a small beam. PV converts light into electric current using the photoelectric effect. Solar power is anticipated to become the world's largest source of electricity by 2050, with solar photovoltaics and concentrated solar power contributing 16% and 11% to the global overall consumption, respectively. Commercial CSP plants were first developed in the 1980s. Since 1985, the eventually 354 MW SEGS-CSP installation, in the Mojave Desert of California, is the largest solar power plant in the world. Other large CSP plants include the 150 MW Sol Nova solar power station and the 100 MW Andasol solar power station, both in Spain. The 250 MW Agua Caliente solar project, in the United States, and the 221 MW Karinka solar park in India, are the world's largest photovoltaic plants. Solar projects exceeding 1 gigawatt are being developed, but most of the deployed photovoltaics are in small rooftop arrays of less than 5 kilowatts, which are grid-connected using net metering or a feed-in tariff. In 2013, solar generated less than 1% of the world's total grid electricity. Photovoltaics in the last 2 decades. Photovoltaics, also known as solar PV, has evolved from a pure niche market of small-scale applications towards becoming a mainstream electricity source. A solar cell is a device that converts light directly into electricity using the photoelectric effect. The first solar cell was constructed by Charles Fritz in the 1880s. In 1931, a German engineer, Dr. Bruno Longhi, developed a photocell using silver selenide in place of copper oxide. Although the prototype selenium cells converted less than 1% of incident light into electricity, both Ernst Werner von Siemens and James Clerk Maxwell recognized the importance of this discovery. Following the work of Russell Lowell in the 1940s, researchers Gerald Pearson, Calvin Fuller and Darrell Chapin created the crystalline silicon solar cell in 1954. These early solar cells cost $286 per watt and reached efficiencies of 4.5–6%. By 2012, available efficiencies exceed 20% and the maximum efficiency of research photovoltaics is over 40%. Concentrated solar power. Concentrating solar power systems use lenses or mirrors and tracking systems to focus a large area of sunlight into a small beam. The concentrated heat is then used as a heat source for a conventional power plant. A wide range of concentrating technologies exists. The most developed are the parabolic trough, the concentrating linear Fresnel reflector, the Stirling dish and the solar power tower. Various techniques are used to track the sun and focus light. In all of these systems, a working fluid is heated by the concentrated sunlight, and is then used for power generation or energy storage.